Thank you, everyone. I'm so glad that there's still so many of you here, even though we're almost at the very end. Yeah, as Steve already said, I used to be an English teacher turned software engineer. And because of that, and because I work with languages, mostly Ruby, JavaScript, bit of Elixir, I never have to think about garbage collection. It just happens. How many of you do need to think about it? Do you need to think about garbage collection in your day-to-day work? That's like, I don't know, maybe 10, 15. Why are you here? But I hope you learned something anyway. Because to me, it has always felt a little bit like magic. You know, I can make all these objects, do all this stuff, and I don't know, usually I don't have any problems and it just keeps going. And really, it's just code, computer stuff, math. And I don't like magic. Well, I like it in the sense of magic shows, but not in the sense that, you know, it's just science I don't understand yet. So hopefully, I can take away a little bit of that magic today and give you a basic overview of what a garbage collector does and how it might do that. I do want to emphasize the basic part, because I only have 20 minutes, so it's a high-level overview, no implementation details, weird edge cases, which I'm sure they're there, but that's not what we're going to focus on. So instead, we're focusing on the 3 things that a garbage collector needs to do. It needs to allocate memory. It needs to tell you where you can put your stuff. You know, imagine you're at a friend's house, helping them put away the washing up. I've got this pot, where do I put it? Oh, the cupboard right there. I've got this fork, where do I put it? Oh, in the drawer to your left. Because to keep track of memory, you need to know where stuff is going to go. So the garbage collector tells you, oh, you want to create this object? Cool, you can just put it right there. That bit of memory, that's yours. Just put it there. Then it needs to figure out if you're still using stuff. Because it can't delete anything that you might still need. But you would like it to delete all the stuff you no longer need. And that's actually fairly tricky. It's easy to find some things that are definitely garbage, but it's much harder to make sure. Sorry, I don't want to breathe into the mic too much. All right, anyway, so you need to find the garbage. You need to know what you no longer need, what you can get rid of, and hopefully don't get rid of anything that you do need, because it's better to use a little bit more memory than it is, you know, for something to just completely crash because you did really kind of need that one thing after all. And I don't know about you, but that's kind of how I clean up. I hold on to things because I'm like, oh, I don't think I need it, but maybe I do. And then lastly, it obviously needs to get rid of the stuff that it has found. Get rid of that garbage. And to talk about these 3 things, I'm going to take you through a few algorithms and strategies that can do this. And we're going to start with one of the simplest ones, which is called reference counting. And it does exactly what it says on the tin. It counts how many references exist to a certain object. Because if nothing points to it, you can't be using it anymore. So let's have a look at a quick example. Let's say I have a very creatively named variable that I called name, and I assign it the value WebCamp. The garbage collector then tells me where I can put it, and says, okay, cool, I've got WebCamp, it's here, and one thing, name, is pointing to it. And another very creatively named variable called otherName will point it to the same thing. And now, WebCamp has 2 references or pointers to it. It's a little bit more complicated than this in reality, but this is the basic idea. And if we get rid of them, we just drop the counter. We set name to nil or null or none or whatever it is in your language of choice, and we take off one of those references. Can do the same thing again. And now nothing is pointing at WebCamp anymore. You can't get to it, and guess what? That means it's garbage. And this is a big advantage because you don't need to stop your program to do this. You know, you can just keep track of it as you go, and as soon as something hits 0, you get rid of it. You move on to the next thing. Python actually uses reference counting for a good chunk of its garbage collection, but reference counting in this simple way has a problem. It has a problem with a thing called cycles, which is when things point at each other or at themselves. So let's say I have, once again, a very creatively named variable, 1, which is a hash or a map, and it has a key called other that currently it has nothing. But the garbage collector has given me, a place to put it, and one thing points at it, the variable 1. Now I'm making another one, which is named 2, which is a little bit confusing. I could have chosen slightly better names there, but please bear with me. And its other key is going to point back at that first one that I created. So now that first one has 2 references. The one that's coming from that other object or that other map, and the one that's coming from the outside. And we're returning the favor because that first one, we're going to point that one right back at number 2. There we are. So now they both have 2 references, 2 pointers. And you could probably take a wild guess as what the problem might be. Because if I get rid of those variables 1 and 2, those go away. There we go, done. But they're still pointing at each other. These 2 hashes are just kind of floating around, and they're still at 1. The reference counter is going to go, oh, cool, you're at 1. You're good, you're still alive, I don't need to clean you up. Where actually, it does need to be cleaned up. Python has other ways of dealing with that, and some of those we'll encounter later, so I'll mention those when we get to them. One of the better ways, there are ways of reference counting more fancy that can help you with this, but we're not going to focus on those. We are instead going to continue on to a different algorithm called Marksweep. And the idea behind this one is if you can't get to a thing, you can't use it, it's trash. You know those things in like the very back of your drawers that you can't even really get to? You might as well throw them out, because how are you going to use them if you can't get to them? So to visualize this, it helps to think of all the objects in your program as a giant graph or a tree. In this case, nice pink boxes. Imagine each of these pink boxes is an object or a value of some sort. And that's just a nice big chunk of memory at the bottom there that is currently full and needs to be cleaned up. So we're going to start with marking, and then we'll sweep. We're going to start at a root. There's lots of difficult, complex ways to determine, the roots of a program. But you can, for example, think of global variables, because you can always get to those, so those are good starting points. We start with the first one. We mark it visited, alive, however you want to call it, and we check if it has any references to other things. It does. It has 2 of them. We pop those on a stack to check later. And then we go through them one by one. Cool, I got to you, you're alive. Do you have any children? Yes, in fact I do. I have 1 child. It goes on the stack, and you go there. Okay, you're alive, cool. Do you have any children? Nope. All right, we can move on. And so on, until we've marked every single object we could get to as alive. As you can see, there's 3 of them left. 1 that is pointing back to each other, a cycle, and 1 just like, all by itself. But those are garbage. And now we move on to the sweeping. Because, we know for a fact we can't get to these, we can't be using them, so they are trash. And the simplest sweeping will just go through all your memory one by one and unmark things so you can check them again next round, and clean up the ones that it found that can be cleaned. This is pretty good because it will detect cycles. A downside is obviously that you do have to stop your program in order to do this. So it might take a little bit more time. And you might see another little issue here. What if now I have a really big object that I want to create? It's really big. I need 3 blocks of memory next to each other. I don't have those, because all I have is 3 little separate bits. And that's where the next thing comes in, which is copying collection, where you can use, maybe counterintuitively, you can copy stuff to free up bigger chunks of memory. And this is only the cleaning up part. We're just going to assume that this top thing of memory, because you split your memory into 2 separate heaps, and you only use one at a time, and you switch every round. We're just going to assume that this top bit of memory, it's full, we've marked or somehow figured out what's trash, and now we want to get rid of the trash. So what we're going to do, because we want to keep everything close together and have a lot of free space, we're just going to copy the live objects over to the other heap. And then we can just throw out the entire top one, which is nice because you will always have the maximum amount of space next to each other to continue. The downside, obviously, is that you really only use half your available memory because you split it in 2, which might mean that you need twice as much memory or twice as often you need to run your garbage collector. So this is usually, I don't know how you clean, this is not really a thing that I would do, although maybe I would. Maybe if I got rid of a bunch of books, I would just move them all to like a separate shelf and put them nicely together so I have an entire shelf free rather than like 2 half shelves. But you don't want to check too often, especially not if you have to stop everything. You don't want to stop the world and do a whole bunch of work every single time while your program is just going there like, excuse me, can I like continue please? All I asked for was like a little bit of memory, can you just like chill? It could. Hopefully, you don't always have to check everything. And that is the last aspect that I wanted to talk about today, which is something called generational garbage collection, which isn't necessarily like an algorithm, it's more of a strategy that you can use. And the basic idea behind it is that if you've been using something for a while, it's probably important and you will probably need it more. You can, for example, imagine if somebody visits a website, you visit a website, your server needs to do a whole bunch of stuff to get that page to the user. But once the user actually has that page, a lot of that stuff is probably not necessary anymore. And you will just do the whole thing again for the next request that comes in. And that's the idea behind this, that objects are very likely to become garbage very shortly after they are created. And if they've been around for a long time, they're probably there to stay. And you can take advantage of that in the same way that you don't have to, if I need to clean out my closet, I don't need to clean the kitchen first. I mean, maybe I should, but you know what I mean? You only have to focus on the things that you need to clean. And to do that, you once again divide your memory into 2 or more generations. Python uses 3 generations for their extra, like the other aspect of their garbage collector. My example is just going to show 2, but the idea is really the same. So the first time an object gets created, you put it in the new memory, because initially it's all new and fresh, they're all little baby objects, until either a certain number of them are created, or your memory is full, if for any reason you need to run the collection. So you run the collection, these 3 survived, they made it, they live to, object around another day, and you fill the memory up again, and you do it again. And these first 2, these are the tough ones. They've already survived 2 garbage collections, so they're probably fairly important. What exactly that number is depends per implementation, obviously, but it is usually a fairly low number. And then what you do, you copy your baby objects, which are now full-grown objects, to the other generation, and clean up the new the baby generation. And in this way, you don't actually really have to look at those old objects very often. You don't have to check them every time, because they're probably still good. You only ever have to check them when you run out of old object memory, or if some rule that you follow for that has been met. With Python, for example, they have a certain number of objects that can get created per generation before they run collection. From the top of my head, it's about 700 in the youngest generation. So every time like a total of 700 new objects have been created, they're like, oh, oops, a lot of little baby objects, let's clean up. And for the older two generations, it's a much lower number, only about 10, which really shows you the difference between how often you need to check those. So I guess in that sense, it would have been better if I'd made the top one a little bit bigger than the bottom one, which is probably more realistic. But the principle remains the same. And in reality, obviously, many languages and everything use different combinations and different fancier versions of any of these or other algorithms. You know, people much smarter than me with PhDs and stuff will think about these things and, you know, make them just like a little bit faster. But at least, hopefully now, a little bit of the magic is gone. I mean, I don't mean to take magic out of your life. That sounds really sad, but at least now garbage collection is maybe a little less magic, and at least like you have a little bit of an idea of, oh, okay, so that's kind of how it works. And I encourage you to go figure out how it works in your language, which strategies it uses. Because Ruby, for example, uses a version of Marksweep in its basic implementation with a thing called lazy sweeping to make it a little bit faster, where it marks everything, but then it sweeps only the bit that you need. Like, imagine, I don't know if you ever did that, but when you were a kid and you're like, you have to clean your room and you just kind of like make a little path, just enough to get to your bed. Kind of that idea. You just sweep what you absolutely need to sweep to get it done faster. And there's many other implementations in other languages that I honestly don't know about, so please don't ask me what does language XYZ use, because I've told you the ones that I know. And with that, I would like to hear if you do have any questions, so let me know what you think, and ask any questions that you have. And if I don't know them, maybe one of those people who raised their hands at the beginning of the talk will know. Thank you.